Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. It's my great pleasure to introduce Professor Baochen Li to give a talk on scaling laws and trade-offs in peer-to-peer live multimedia streaming. Professor Li received his PhD in year 2000 from UIUC. He is currently with the Department of Electrical and Computer Engineering in the University of Toronto, and he is an associate professor. He holds the Bell University Laboratory Chair in Computer Engineering. In 2000, he was the recipient of the IEEE Communications Society Lenoid G. Abraham Award in the field of communication systems, and his current research interests include network coding, peer-to-peer networks, and wireless networks. Without further ado, let's start the talk.
Thanks, Jane. So the talk today will be on scaling laws and trade-offs of peer-to-peer live streaming. And part of this talk is kind of a joint work in the upcoming ACM Multimedia 2006 paper. And this is a joint work with Tara Small, who is our PhD postdoctoral fellow, and Ben Liang, who is the co-supervisor of the postdoc. This talk will be a little bit unconventional in the sense that will be, the first half of the talk will be less technical in the sense that I would like to offer some of my views on the general advantage of peer-to-peer networking. And then I'm going to progress into the motivational part of the actual technical content in the second half. So the first question I would like to kind of explore a little bit is how can peer-to-peer help? It looks like it's obvious, but there are tons of technologies out there. Web 2.0, Windows Live, Google, YouTube. This slide is written before Google and YouTube become the same thing. BitTorrent, iTunes, and Skype. All of these things are, live there. They're currently being deployed, and tons of things being done there. But some of them are using peer-to-peer networking. Some of them are not using peer-to-peer. So exactly what is the key advantage of peer-to-peer? I would like to start the talk with this question. So one quote that I have from the May issue of 2006 from Business Week is BitTorrent recently signed in May a deal with Warner Brothers to distribute movies, and the actual idea is very obvious. The actual idea is that it will be prohibitive to actually try to use the server bandwidth to actually distribute movies and television programs. So Hollywood would like to explore alternatives of using peer-to-peer technology, and BitTorrent as a company is one of the obvious choices. So the conclusion from that observation and some of the previous other instances would be that peer-to-peer helps to dramatically save bandwidth cost on the server side of content distribution by shifting the burden of the bandwidth from the server side to the home broadband connections. So because we have ubiquitous usage of home broadband, DSL and cable modem connections, we would like to use the idle upload capacities there to actually save the bandwidth costs on the servers. And that's how peer-to-peer actually can help. So from that point of view, I would like to have the first observation. The first observation here is the key benefit of peer-to-peer architecture is the saving of bandwidth cost. And it is applicable to downloading, to video streaming, including on-demand streaming and live streaming. And the case in point here is that without this kind of help from peer-to-peer, it is very unlikely for big companies, even companies with top dollars, to launch a live popular webcast. Let's say something of a major event. It doesn't have to be even as major as a World Cup or Super Bowl. It's just some kind of a big major conference. Live webcast is not usual these days. And that comes with the second observation. Second observation is that DHT-based peer-to-peer structures is to become marginally useful. By marginally useful, what I mean here is probably it's not very useful. And the reason here is that even though there exist so many previous papers and past research effort on using peer-to-peer for some kind of a serverless search, it turns out that all of the search and queries and user authentication can be done and can be very efficiently done on the server side, on huge servers, because the actual cost here is CPU, and CPU is not really like a big deal here. And there are tons of successful examples: Google, iTunes, Flickr.com, YouTube, BitTorrent trackers. All of these are good examples that we don't need search on a peer-to-peer fashion. We can do search in huge servers. And the same fate applies to all the previous research on unstructured peer-to-peer search, which means that we would like to do, instead of an organized, structured DHT-based search, I would like to do random walks or flooding the queries like Nutella to actually search content in a completely decentralized way. And that's something that I believe is not realistic because of the huge server capabilities, or anything related to distributed publish subscribe. These are all variations of unstructured search. So the third observation that I have here is that the trend is probably, this trend of using broadband, home broadband connections is probably bad news for the residential broadband providers, for the ISPs that provided them. So this group of companies, they argue against network neutrality, which means that they would like to charge the content providers for this cost of bandwidth instead of charging the users. It's unlikely for them to actually charge the users because it's always a flat fee scenario, like a flat monthly fee. Without that, they're easily out of business. So they would like to shift the charges to the content providers. However, that debate is non-technical. And that debate does not have a certain outcome. So we'd like to leave it out of the technical picture of the rest of this talk. So with these observations, the question is peer-to-peer or not. Do we want peer-to-peer or do we not want peer-to-peer? Let's first look at the facts. So there exist websites that take advantage of peer-to-peer technologies, except for Skype.com, which is more international. The rest of them are mostly in China. And there exist also websites, mostly in North America, that hosted in North America, that so far have not started to use peer-to-peer technologies. We can also observe that most of the websites using peer-to-peer, they're using peer-to-peer for live streaming sessions. And most of the websites that does not use peer-to-peer, that they're actually trying to do on-demand streaming instead of live streaming, or just we can call it simple downloading of short video clips. Yes?
So do you consider the services that Akamai provides to be in the same category?
In terms of peer-to-peer?
Mm-hmm.
Well, that's kind of too broad of a definition of peer-to-peer. My kind of a more stricter definition of peer-to-peer is that we would like to use home users' bandwidth. Instead of trying to say, let's just put it like a broad definition, like tons of servers in a fully decentralized way. They can organize their efforts and launch the efforts together. So instead of a centralized versus distributed, I would like to limit the definition of peer-to-peer by taking advantage of home broadband connections.
Why?
Because that is the whole point of using peer-to-peer.
Well,
the whole point of using
increased bandwidth or on-demand bandwidth, etc., and that's a service that Akamai provides. So tell me how you, maybe I answer this question differently. Akamai provides a set of services that are what they call peer-to-peer, distributed, decentralized, to enable on-demand greater capacity for people who need to distribute files.
Right.
Okay.
Right.
So how does that differ from a facility that would be a home peer-to-peer network?
Well,
I don't mind if you want to separate them and talk about them,
right.
but I would like to know, just defining them out doesn't help me if you can't tell me why it's different or how the services would be different.
Well, so I think there's a difference in bandwidth availability. So they have, if you call Akamai peer-to-peer networks, they have tons of bandwidth, across the board for all the servers to talk with each other. Now, if we talk about peer-to-peer, most of the peers using home broadband connections, they don't have as much bandwidth. They have probably a few orders of magnitude lower bandwidth. So it takes to take advantage of this kind of bandwidth is harder, but it makes sense in the sense that anyway, they're actually wasted. So we would like to take advantage of the wasted bandwidth there collectively to actually help to save the server bandwidth. In fact, the best way to use the home broadband connections is to actually launch a combination of Akamai kind of CDN type of network and use also the wasted bandwidth, upload bandwidth on the peers. So the combination of the two is a must. It cannot be just one server and tons of peers, or it cannot be just downloading from the actual decentralized system of servers without using the upload bandwidth. Especially as we can see in the event of live streaming sessions.
Do you see? Did that answer your question?
We can continue the
Yeah, I'll
questions.
watch the rest. Yeah. So I'll wait for the rest of this, and we'll see.
We will see. Yeah.
So just a short question. Do you see that the society as a whole uses more resource or less resource if you use a peer-to-peer like content distribution versus a server-based distribution?
Well, they use the same amount of resource because if given a fixed number of users using the current, let's say, channel, the streaming channel, then everybody's having about the same streaming rate. So collectively, they use the same amount of resource. However, you just shift the burden from the server side to to utilize the upload capacities of the peers.
Modular the signaling, modular the control channel and signaling bandwidth that has to be exerted to maintain the peer-to-peer system.
That could be one of the overhead of using the peer-to-peer system. Yes. But given if we have a small overhead there, then we can actually take advantage of the upload bandwidth, and that I perceive is one of the main advantages of peer-to-peer. The rest of the advantages are not as obvious in terms of saving bandwidth costs on the server side. But still, as you can see, still the answer is not very clear on exactly why should we use peer-to-peer and what is the exact circumstance that peer-to-peer might be helpful. As you can see, there are websites and systems using peer-to-peer and there are systems not using peer-to-peer. So it's very hard to say at this particular point. But if we actually try to shift any websites from the right-hand view to the right side, to the left side, then the benefit here, I believe, the motivation is bandwidth cost. It's not anything else. That's my own personal opinion. So given all these possibilities of shifting to peer-to-peer, the concern here is live peer-to-peer streaming. So it turns out that from the previous slide's observation that tons of websites that actually took advantage of peer-to-peer, they're actually trying to use peer-to-peer for live streaming. So it looks like live streaming is probably the most likely scenario where peer-to-peer might have worked. So how about on-demand streaming? On-demand streaming being just downloading, kind of streaming short video clips. There are obvious differences between live and on-demand streaming, but if we have, assuming we have a technology already developed for live streaming, then on-demand streaming can use exactly the same way to take advantage of the uploading bandwidth of peers. So in this particular talk, we are actually concerned with live streaming. So we're not kind of trying to say dispose for live and on-demand. We're trying to say let's put our focus on live streaming and see what happens with peer-to-peer. So there exist benefits of peer-to-peer that I've just discussed. There's the saving of server bandwidth cost. No matter if you have one server or hundreds of servers, collectively you save the bandwidth cost on the servers. And there also you increase the maximum number of peers that can be supported, given a fixed bandwidth cost. So exactly what is the catch? So it looks like there exist benefits. And what is the drawback here? What's the downside? What do you think is the downside here? What exactly, why don't we immediately jump onto the peer-to-peer bandwagon. And I believe that there exists another parameter that is not completely overlooked, but kind of not extensively discussed in previous research in academia. And that exactly is the the scalability to the millions of users. And that's something that we have not previously discussed. So given the particular bandwidth cost, and given, let's say the best way to take advantage of that bandwidth cost, how can we scale? Can we scale to an unlimited number of users, or what's the maximum number of users can we actually support? And that's one thing that is important. The other thing that is important is the understanding of the effects of peer dynamics, which is not extensively discussed in previous literature, or they're kind of discussed, but in a kind of a limited system model or a limited set of assumptions. By peer dynamics, a lot of papers call it churn or peer churn or no dynamics or whatever. But it means that we're trying to consider the departure and arrivals of peers as a rule instead of an exception. So we need to understand exactly how peer dynamics affect the actual system. It looks like it's obviously a downside of maintaining the stability of the peer-to-peer system, but exactly what is the effect? So these are, some grand objectives. Obviously, this talk does not intend or does not have the means to solve all of these problems, but these are, future, I think, promising research directions that one should go. More specifically, in this particular discussion, I would like to understand the trade-offs among several very key parameters. The first parameter is the server bandwidth cost that we have mentioned. Since peer-to-peer saves server bandwidth cost, that is one of the parameters that's very, very important. And the other thing that is very important is scalability. What's the maximum number of peers can we support with a particular bandwidth cost on the server side? And finally, I would like to introduce this parameter, which is the delay. I'd like to call it delay. But it's really, some kind of a notion that characterizes the maximum number of streaming hops from the server, which is controlled by, a central company, to a particular peer. And I'd like to take the next slide to take a look at this delay and exactly what does it mean and exactly why is this important. So what is the problem with more streaming hops? So if I have 100 streaming hops from the server to the peer, exactly what is the problem there? And I argue that the problem is that affects one key parameter, and that key parameter is the difference between the playback time and the time when the live event occurs in the original media stream. So if you have World Cup and there's a goal there, does it take 2 seconds or 2 minutes for the peer who is watching the live webcast to actually see the goal and celebrate it? So the idea here is that I don't really have a good word for this particular parameter, and I searched previous literature; they don't have a consistent word for that. So I just call it delay in this talk, but you can call it lag time or anything like that. But the idea here is that I firmly believe that this parameter is introduced by having larger number of streaming hops from the servers controlled by the companies and the actual peer itself. So I believe that it is an important parameter, and if you have more streaming hops, kind of a longer path from the server to the peers, you're going to have a higher delay as defined here, right here. Well, some of the people from the industry, they may not argue that this is important. So some people say that it is actually not that important. Let's say you have 1 minute or 2 minutes in terms of this kind of delay. What's the matter? What's the problem here? Now, it is not really a problem for on-demand streaming. But for live streaming, if you have some kind of a feedback channel, for example, if you have users trying to vote for your favorite superstar right after the actual song, then that feedback is going to have to be instantaneous. So in that particular situation, it is important. However, in some of the other live streaming, it may not be that important if you have 2 minutes or something of delay. But here I believe that this is one of the things that is the downside of using peer-to-peer streaming. So let's take it from a different point of view. And the different point of view is to take a look at extreme cases. Yes?
What do you consider to be acceptable delay?
So that, of course, is depending on the actual stream, the content, right? If it's a World Cup, the acceptable would be probably less than 30 seconds, right? And if it's something that is just a pure television channel that you watch on your evening news, then it could 2 minutes, 3 minutes is not a problem at all, right? Nobody cared about that.
So if you tolerances for something like 30 seconds,
right?
I mean, that seems to support a fairly significant number of hops. So what's your
not necessarily. Not necessarily. I'm gonna come back to that issue, but not necessarily. If you so far I think I probably know a thing or two about the peer-to-peer in the real world instead of only in academia. But so far I have not seen any real-world peer-to-peer live streaming systems that can actually make it less than 30 seconds. So not necessarily that you can actually support a maximum delay of less than 30 seconds with, let's say, a fair number of hops. So if you limit yourself to 30 seconds, it's actually quite limiting.
And there are situations that you may want even tighter delay constraint.
But I'm gonna mention that a little bit, a bit more in the upcoming several slides. I'm gonna mention that a little bit more. So the server serves all the peers directly, and that's one extreme. It's the extreme where we don't care how many servers are there. We can have 2,000 servers out there, but any peer who join the system are going to be served by one of these servers directly, and that's one extreme. The advantage is no delay except for a little bit of buffering delay on the peers. There's absolutely no delay. There's one hop, and the disadvantage is that if you want to accommodate more peers, you have unbounded bandwidth costs on the server, so you're going to have to pay more on the server bandwidth. And obviously it's not scalable in the sense that presumably you don't have unlimited monetary resources on the server side. You cannot scale to unlimited number of peers. On the other side, on the other extreme, no matter how many servers you have, you only serve one peer. That's what you do. And this peer relay the traffic to other peers, and the other peers in turn relay their traffic to other peers. And the advantage is that you minimize the server costs, since you're only serving one peer here. And the disadvantage is the playback interruptions that might be the result because of the insufficient bandwidth. Some of the peers, they may not have sufficient upload bandwidth to serve even one peer. So you you have playback interruptions right there. And then you have unbounded delays, because as you have more peers joining the system, since the server can only serve one peer, it adds up to the number of hops, the distance from the server to the last peer, and it's also not scalable in terms of the amount of delays that you actually introduce to the system. So one side is not scalable because of the bandwidth cost that is prohibitive. The other side is not scalable because the delay is prohibitive. So no matter what, the two extremes may not be the right idea. And most of the current systems, they operate on the extreme on the left side. So basically they have peers directly contacting the servers and try to stream from the server. That's why we have not seen yet too many long video live webcasts from the server, because whenever you have a flash crowd, the server cost will be very prohibitive. And even some of the companies that is large enough to afford something like this, probably they're not willing to host such a live event. For example, if you have a very important conference, like Adobe Photoshop conference, you don't have the live webcast for that particular conference simply because of the server costs. So there are several questions from the kind of a motivational discussions that we have in the previous slides. The first question is, I would like to, evaluate the optimal scenario. Given a certain bandwidth cost, what is the maximum number of peers we can put into this session that this certain bandwidth cost can be supported, can support this maximum number of peers? The next question is, exactly if we can assume that a peer can tolerate longer delays, exactly how much can the server bandwidth cost be saved So obviously, if we can have more delays, we can serve a little bit of bandwidth cost, but exactly how much the cost can be saved. And finally, if we consider pure dynamics, given certain server bandwidth costs, given a system with, let's say, 2 or 3 million users, what is the probability that a new peer would be denied service? You know, the peers, they come and go, let's say, according to a particular probability distribution. What's the probability that this peer will be denied service? So these are the questions we're kind of trying to answer with some kind of a theoretical analysis in the particular system model. And that is the kind of the main concern of the paper that is part of the talk, and that's the ACM Multimedia 2006 paper that I'm going to try to briefly discuss here. So in the upcoming discussion that I have, I try to avoid equations. Even though the paper itself is purely theoretical, almost purely theoretical, I try to avoid equations and try to give you the intuitive sense of answers to this question, and give you some examples in terms of numerical examples on the result of computing these numbers by using the result of the theoretical analysis. So there exists some previous work on topology construction. As you can see, the answers to these questions are very related to the actual topology that we have in the peer-to-peer system. So if you have a different topology, like the topology where everybody connects to the server, then obviously you have higher bandwidth costs and shorter delays. So to kind of try to reconstruct the topology to something else is critically important to answer these questions. And there exists tons of previous work on topology construction. Some of them call it neighbor selection. Some of them call it something else. But there exist the tree-based or multiple tree-based topologies. Any of the application multicast, they're actually tree-based. There's the split stream, which is multiple trees, bullet, multiple trees, chunky spread, more of a mesh-based. Randomized topologies is cool streaming, and all of the real-world protocols. If you go to Wikipedia and take a look at PP Live, it's actually a randomized topology as well. So all of the real-world protocols currently in operation, they're actually randomized topologies, in the sense that they try to randomly pick who are the peers that they should connect to, and randomly drop them if the quality is not good enough. There also exists some kind of work in previous literature talking about directed acyclic graphs as topology choices, but relatively fewer work in this particular area. So let's take a look at the kind of an example of what kind of a tree-based strategy that do we have. This is what we have back in 2000 to 2002 when the application layer multicast trees are kind of in full force in research community. We'd like to build something like this as a topology. As this is an example of the tree-based topology. We assume we have 13 nodes, and we assume we have a server, which is the node 0, tons of bandwidth out there with the server, and serves a bunch of peers. However, each one of the peers only had one parent serving this particular peer. And finally, the leaf peers do not serve anybody else. So that's the tree-based topology as an example. Very simple example here. Here's an example of the randomized topology. This example, obviously, just using a very simple simulator, randomly generate a particular neighbor selection of each one of the peers, and just try to draw the actual resulting topology here. As you can see, we have the same 13 peers, but they're organized in a completely different way. The server is in contact with a bunch of peers, and some of the peers contact some of the others. Each peer might have more parents, they have more children, they could have more children. And it's completely unorganized in the sense that we don't have any guidance at all in terms of how do we actually try to construct this topology. We try to do it randomly.
Why the arrows go back and forth? Why there are two arrows?
Well, it's kind of a bidirectional in the sense that one peer is serving one block to the other peer is serving a different block to the previous peer. Okay. So if you consider the stream as different blocks, they serve different content back and forth. So there's no kind of very strict relationship between who is really serving who. They're actually serving each other.
So it links back to the server or just artifact?
I believe so. That's just the artifact of the actual simulation, of the actual randomized generation of the protocol.
Special meaning here?
It doesn't. It doesn't have any special meaning here. It's just a illustration, visual illustration, how it's different from the tree-based. So as you can see that most of the real-world protocols, they're using this random topology, and some of the previous academic work, they're actually using the tree-based, some of the other using randomized, such as cool-streaming. And the question here is that, these two different strategies of constructing topologies, are they the best that we can do, or are they the optimal that we can actually achieve? Do they save, maximally save server cost? And do they introduce the minimum delays from the servers? So the context of analysis is pretty general. I tried to make it so that it's pretty close to the real world, even though if you have any analysis, there's no way for it to be exactly the same as the realistic case. But we assume that we have one server, but it's equivalent to more than one. Because if you have one server with 2,000 bips of bandwidth, it's equivalent to have 10 servers, each one of them with 200 megabits of bandwidth. So it's equivalent to have more than one. And we assume we have a number of peers in the system. We are concerned with the total bandwidth cost of the servers on the server side, because that's very important. We'd like to save as much as possible in that category. And we are concerned also with the delays. And the delays obviously are longer when you have more hops from the server to the peer, to each one of the peers. We call it propagation and queuing delays. Try to divide the delays into two different categories for each one of the hops. The reason here is that we'd like to consider the difference between just the delay of transmitting the actual block from one node to the other, and the actual delay of having the block here in the node, but just buffering and queuing up, and kind of before it's actually being transmitted to someone else and being played back. And finally, we assume the streaming playback rate of P, which is mostly the case in the current real-world scenarios. So we also take a few assumptions on the upload capacities of the nodes. First of all, in terms of topology construction, we have absolutely no restrictions on the number of parents, number of children that this peer can actually support and be served. And each peer has a maximum upload capacity. That's what we assume, because we're here mostly concerned with kind of home broadband users and DSL and broadband and cable broadband users. So we kind of assume that this maximum upload capacity is drawn from a probability distribution with a particular mean upload capacity. However, we do not put any restrictions on the actual distribution that we can actually have here. So we also assume that peers can use up all its upload capacity. If there are background traffic, let's just assume they not exist, or if they do exist, that they have a low priority, or if they do exist, when we take a look at the distribution, we already take them into account and exclude background traffic, and we know exactly how much upload capacity that we have for each one of the peers, excluding that background traffic. That's the actual assumption here, and peers can use up all of its upload capacity. And we also have a kind of a strong assumption here. I believe it's the strongest assumption in the set of assumptions that we have in the system, that we don't have any worries on things like, how do we schedule them, especially which block should I send, which block should I receive, what's the optimal scheduling algorithm, the deficiencies of a suboptimal scheduling algorithms. The reason why we kind of make this kind of assumptions is that we like to take more realistic concerns of a protocol design out of consideration, out of the picture. We assume schemes like things like network coding, any kind of coding schemes is perfect, is mature, is good enough to be used in the real world, so that it eliminates any of the the exchanges of buffer maps and scheduling algorithms and so on. Obviously, this is not realistic. Right now, things like network coding is not mature, is not being used, and cannot be replacing the kind of scheduling algorithms of exchanging availability information. But we kind of assume that that is the case. So no worry on any of the protocol deficiencies. So let's continue and take a look at the kind of the characteristics of optimal live peer-to-peer streaming protocols. So in terms of the optimal peer-to-peer streaming protocols, I would like to take a look at the objectives of what do I mean by optimality first. So I would like to think about exactly what do I mean by this. And one of the things that I should try to take into account is an optimal topology should try to minimize the server cost if we give a particular constraint on the number of hops or the delay from the server to the peers. Number two, we can actually try to say, to achieve something like this, we need to maximize the contribution from the peers in terms of bandwidth. So, this is obvious. This is intuitive. If we have more peers contributing bandwidth, we, save more cost on the server side in terms of bandwidth. So that's obvious. However, given the particular server cost, if we try to maximize peer bandwidth contribution, that objective is actually equivalent to minimizing the delay. So if you have more peers contributing bandwidth, then you have shorter hops that you have from the server to the, the last peer in the topology. This is also intuitive because if you have more peers have more bandwidth in total collectively, then you can actually, for each peer, you can support more peers, which flattens the actual hierarchy from the server to the actual last peer in the hierarchy. So all of these are the same thing. We want to minimize the server cost. We want to maximize the contribution. We like to equivalently minimize the delay. They're all the same thing. And all of these are objectives of optimality, of an optimal streaming, peer-to-peer streaming. So one thing that we started with is to basically take a look at the actual queuing delay. So this is the buffering time. Everybody have a playback buffer. You receive something, you receive it in the playback buffer. There's some variations and fluctuations in bandwidth. I'd like to use a playback buffer to smooth it out. And we'd like to conclude with a very simple intuition that such a buffering delay, what we call queuing delay, caused by this kind of a data buffer that you kind of use as a safety net for streaming. In optimal case, this is not a concern. There's no need to there's no need to consider this kind of a buffering delay. For optimal session, if we have unlimited length of playback, of this live streaming, this queuing delay can be treated as 0. So the intuition here is that even if this is not 0, this should be, if you have a streaming playback rate that is higher than your download capacity, than all the upload collective upload that all your parents are serving you, then your buffer will gradually be going to 0 because you're emptying your buffer, and eventually you will be at 0. So at optimality, everybody will be 0 because that's how we can actually operate this. So in this case, what we can conclude is that we can only care about the propagation delays, which is a strict function, linear function of the actual number of hops from the source to the number of to the actual peers. Obviously, in reality, this is not the case. In reality, everybody still had some kind of a playback back buffer in some kind of a queuing delay before this buffered block after it's received and before it's actually being served to someone else. So there's still some kind of a queuing delay, but that's the reason is that in reality, we don't have optimal streaming. Optimal streaming is a benchmark that it cannot be reached in reality. And that benchmark, even though theoretical, is exactly what we would like to explore in this particular work. There also something that I would like to mention in terms of the propagation delay. Not the buffering delay, but the propagation delay, in the sense that, what is the amount of time that you try to consider from one node receiving a block to its downstream children receiving the same block? And that's the propagation delay. So obviously, you have to take into account, the transmission time of the actual block and the time for the actual packets to propagate to the next hop. But my conclusion is that that is not something that we should be concerned about. That is in the in the order of magnitude of a few hundred milliseconds max, and that's not something that we should be concerned about. The reason is that because of the inefficiency of the protocol, introduced by the lack of perfect knowledge of block availability. So I don't know at this particular point who has the block among my parents. So I'm going to have to do something to actually get that knowledge. And that's something to be done inside the protocol. And that is something that wastes time. And that time is something that we would take into account in the propagation delay. So I'll give you one very good example, which is the buffer map exchange, the block availability exchange. So before we know that the block exists in a particular parent, we need to actually have the buffer map of that particular parent. And that kind of exchange cannot happen in real time. You cannot say the parent immediately had that block, immediately advertised to everybody that it has the block. It has to be exchanged periodically. And the shorter the period, the more the messaging overhead in terms of the protocol, additional protocol overhead in peer-to-peer protocols. And the longer the period, the less overhead you introduce. However, the longer the period of exchanging this buffer map, the longer the propagation delay do we have for a block to be available from the parent from that particular point to the point that the block is available in the children. Yes?
Sorry, not sure whether I got this. So, but if I'm a node and I have to send the same block to 2 or 3 children,
right,
then I mean it's impossible for me to send this block to all of them at once. I kind of have to buffer this block, and this seems to be. So do you abstract this away, or so I didn't get this point.
So we abstract it away in the sense that you can send to all of them at once, but your only constraint is the upload capacity, which means that you send you send to all of them at the same time if you have the same you have for example twice or 3 times the streaming rate in your upload capacity. So you can actually send at the same unit time. Yes.
But buried in this is actually a very different assumption, which is that you don't proactively send blocks to anyone. You only send blocks when effectively you are certain that that other party needs it. Or conversely, you're not registering block subscriptions with your upstream neighbors. But it's a pull model, not a push model.
Here it is kind of assuming a pull model. But a push model is kind of like a pull model plus subscriptions, so it's about the same thing. But
doesn't that change the parameters around what your
it kind of shortens a little bit on the propagation delay, but it's still not in the order of hundreds of milliseconds. So you cannot get it. The availability of that block or the information that I need that block cannot be obtained within a few hundred milliseconds. So unless you have real-time exchange of availability of blocks. So my argument here...
To exchange the availability of block information at all, right? You're assuming that you need to do that block availability exchange.
That's right. If we consider the inefficiency, I'm assuming I need to exchange block availability. Yes. In the strict static topology with the strict parent-children relationship and with the directed cyclic graph from the server to the peers, then you could assume that you have absolutely no exchanges. In that case, the propagation delay could be very short, could be much shorter. But here, in reality, in kind of those kind of existing real-world peer-to-peer protocols, the inefficiency of protocol exchanges of buffer maps introduces much longer propagation delays in the order of seconds. For example, a few seconds per block per hop instead of a few hundred milliseconds per hop. So that is a key downside of propagation delay. And if you have, let's say, 10 hops from the server, and if you have 5 seconds to know exactly that block existed, then each hop will have 5 seconds, and 10 hops will be almost a minute. And that's exactly why in the current real-world protocols that are currently in operation, I've never seen anything that has a delay that is less than 30 seconds. Delay being the definition of delay is actually the difference between live event happening and the time that you get that live event.
I guess I don't want to rattle the rest of the talk, but so we can take this offline.
But this is very important.
I would actually argue that that's a flaw in the design of those systems, not a fundamental property.
It could be, but I don't know yet. So it could be a flaw of all of these existing implementation of protocols, but I don't know yet. I don't have a better solution to that problem because they use randomized topologies and so on. Because that's why they have to exchange buffer maps. But we could have a more organized way of constructing topology. That's a very valid point. But I do not have a solution to that point yet. But here, obviously, this entire discussion has no dependency on how long the propagation delay or how short the delay is, because here we're only concerned about the number of hops that we have from the source to the actual peer. So one thing that I basically have concluded in the theoretical study, given the context of the analysis, is that in an optimal session, assuming optimality is defined as the previous slide, with certain bandwidth available from the server, fixed amount of bandwidth cost, peers with upload capacities following a particular distribution, any distribution would be fine. It is actually a good idea to push peers with higher upload capacities closer to the source, with shorter streaming hops, because we show that if we do this, it achieves optimal performance for the session, which equivalently means minimum delay, average delay for all the peers. So if we have some way to organize the topologies, instead of a completely randomized way of organizing topology, we should push the peers with higher upload capacities closer to the source. Whoever who have 100 megabits per second in terms of upload capacity, we should make it exactly the same as just directly connecting to the source. Whoever who had less and less and less, we should put them further and further away from the source. And if we have perfect knowledge of the entire system, this is the way to construct this kind of optimal topology. And something that we can derive immediately from that lemma is that in the optimal session, there should be no peers that are more than one hop away from the actual server, and these peers receiving any bandwidth from the server. So the server are only serving the peers that are one hop away. They're only serving the peers that are directly connected to the servers. All the rest of the servers should be served just by these one-hop peers directly. So we should never have a situation in the optimal session where a particular peer that is 2 hops or more than 2 hops away from the server is served directly by the server just to make up for the bandwidth deficiency from its own parent peers. If we have that particular case, this is not an optimal session. An optimal session never had that happen. So this combined with the previous lemma shows that we should try to use the servers just to serve our high bandwidth peers instead of serving any random peers that we selected. The other thing that we have concluded is that previous conclusions are assuming that we have any arbitrary upload capacity distribution across all the peers. But if we have an upload capacity distribution that is just a simple constant, everybody had the average upload capacity, that actually leads to the worst performance defined by the greatest average delay in the actual session. This is actually the worst as compared to any other arbitrary distributions, if everybody had the average. This is actually interesting in the sense that if we have some variations, so if we have variations in terms of upload capacity, which is the case in the internet, in the current internet, it's actually a good idea. It's a good news in the sense that it will lead to better peer-to-peer performance, topology performance, as compared to everybody had exactly the same upload capacity. So we need variations. We need some kind of fluctuations. So from the previous kind of theorems and lemmas and corollaries, obviously I'm skipping all the proofs, but exactly what does this thing look like? So as compared to a tree-based topology or a random-based topology that we have previously shown as examples, this thing looks like this. It looks like if we have tons of good peers, which peers with high bandwidth and tons of upload capacity, they should be directly served by the server, no matter how many servers we have. So the big black 0 could represent all of the servers that are currently in control by the company. And then these peers will be serving other peers in turn serving other peers. But if we assume that the streaming rate is greater than the average upload capacity, by average does not mean that it's greater than all of the upload capacity. It's just the average of the distribution of upload capacities, which means that some of them had higher than the streaming rate, some of them had lower. Then we require more than one peer serving a particular new peer that joined the system, which means that this kind of an inverse tree kind of scenario will get thinner and thinner as we go to the bottom of the tree. Yes?
Could you remind me what is the optimal streaming session again? And let's say you know the bandwidth of all the peers. How do you devise this architecture?
So the optimality is defined as minimizing the bandwidth cost on the servers, or equivalently, maximizing the peer-to-peer the peer bandwidth upload capacities, the contributions from the peers, or equivalently, minimizing the delays from the server to the peer, the average delay from the servers to the peers. So the well, if you have peers that are contributing more of their bandwidth, right, then obviously it saves the server cost because this does not cost the server as much. And then for peers that contribute more, they can serve more peers, which means that you're trying to kind of flatten the levels between the servers and the peers. So which means that you have fewer levels in the actual topology, and that kind of minimizes the average delay.
Can let peer contribute more without flattening levels?
Well, the peer contribution is already there. We know the distribution. So the distribution is there with a mean upload capacity. So it's just a matter of how we organize these things, how we're going to put them in the topology. Where should we put these peers in the topology to construct an optimal optimal session so that the peer contributions is maximized. So that's the only purpose. We're not changing the peer contributions here. The distribution is fixed, it's known, but it's arbitrary. So it looks like this, even though it's purely theoretical, obviously we don't know the actual upload capacity distributions. Yes?
So in this figure, it seems that 5 does not get anything from the top layer.
That's right.
It only gets from 2, 6, 10.
That's right.
Is that always the case? I mean, will 5 sometimes get things from the top layer?
Well, it's not prohibited in the sense that in the context of the analysis, it's never prohibited. Anybody can get from anybody else. But if we actually try to construct an optimal topology, this is the way to actually do it.
So you mean in optimal sense, it has to be this layered structure?
That's right.
There's no cross layer.
That's right. If you actually discard all the rounding problems in terms of dividing the upload capacity by the streaming rate, you get to 3.14. That's a rounding problem. If you discard that sense, then this is the way to do it.
That seems not natural because if I reduce the upload bandwidth of 10, right, at some point 5 will need to get something from the top layer, right?
Right, but here we are not considering any kind of cases where the total upload cannot meet demand of the total download.
Can still meet the total demand, but I mean the second layer is not sufficient to provide 5's demand. Then it has to get from the first layer, right? So yeah, I guess.
Yeah, that's what I call the rounding error. So if you have like 3.14, which I'm still missing 0.14, then I have to get from someone else. If that's the case, then we can actually try to connect with a different node in the upper layer. But this shows that we don't want to have lower layers connecting all the way to the servers, and we want to organize them so that we have sufficient amount of bandwidth on the second layer to serve the third, and sufficient bandwidth on the third layer to serve the fourth. Yes.
So I have an observation. For node 2, for example,
right,
they are served by 5 upper layer nodes.
Right.
And 5 is served by 3.
Right.
Does that mean that the upload bandwidth of 2 is higher than 11, perhaps? Because it actually can upload a third of what 5 needs.
Well, but the 11 is serving both 2 and 6, which means that, and 2 is only serving one node.
Oh. Okay, I see.
So that's basically just how it looks like. It doesn't look like a tree and doesn't look like a random topology. And the key insight here is to push the upload capacities that are higher to closer to the source, if we can actually do this. Yes.
Does that mean, though, that the people, this implies two things to me. One is that the people at the lowest levels, in order to get higher reliability, they're actually going to have to connect to a larger number of parents, because each person at the lower level is consuming a higher percentage of each parent's upload bandwidth.
Right.
Right. Which means
exactly
that it's at higher risk of having that bandwidth getting,
if we have dynamics, yes.
Right. So each low-level person has to maintain more connections than higher-level nodes.
If we consider dynamics, yes. Here we consider only a static topology without any dynamic. Nobody's leaving, nobody's joining. If we consider that, then we would like to ask the question: how are we going to organize it optimally?
There's also the dynamics around capacity, because capacity also is not static.
That's right. So if we consider more reality, then we don't know the capacity upload distribution. We don't know, if we do know, it changes over time. So that's something that is the case in reality. However, it still does not change the conclusion where, the best way to organize this is actually push higher bandwidth nodes closer to the source instead of leaving them randomly organized.
The other question is, this also ignores network locality as a thing that you would potentially want to optimize for.
The network locality is more related to the delay. So it's more related to, how long does it take? Is it 300 milliseconds or 10 milliseconds for one server to going to the other, for one node going to the other node? In terms of this analysis, we do not consider that because we assume that we know the upload capacities, and that's different from the network locality. That's bandwidth instead of delay. So this is something that we kind of considered. And then like to take a brief look at the resource performance trade-off. So in terms of resource performance trade-off, the resources obviously are the bandwidth cost on the servers, and the performance is basically delay and the maximum number of peers that we can actually support. So first, in the actual work, we developed a way, we have 2 pages in the paper to develop this way, but we actually developed a way to compute the number of supported peers with certain server bandwidth and arbitrary peer upload bandwidth distributions. So we can actually try to put in a closed form equation, given this kind of a context of the analysis, given known capacity distributions and given a certain server bandwidth, we can actually compute the number of supported peers. What's the maximum? So let's take an illustrative example. So for example, if we have peers upload capacity following some kind of a zip distribution with an average data rate of 200K bits per second. And the server had, let's say, 500 megabits per second. Let's say the streaming rate is 250, which is more than 200, which is the average upload capacity, which means that the shape of the topology will look like exactly like the example that we have previously shown. And let's say we expect 80,000 users in the flash crowd scenario. And let's see exactly how many users can we support if we organize them in the optimal way. And the result of computation is that if we have just one hop, the top 16% of the upload capacities will be served. And if we have 2 hops, then the top 58% will be served. 3 hops, the top 81% will be served. And if we go to 4 hops, only increase a little bit, 82.3. We go to 5 hops, only increase it just tiny little bit at the second digit after the decimal point, and then it's unable to serve 18% of the demand if we have 5 hops. And if we increase more hops, it doesn't work because the peer bandwidth, upload bandwidth with more hops, they're just minimal. You cannot use them to serve anybody. Yes.
In your analysis, do you assume that the upload bandwidth of the bottom layer is wasted?
Yes, we do that. Yes, yes. But they're wasted in the sense that they're just so minimal that probably we cannot use them to serve anybody anyway, because we have very few peers at the bottom and their upload bandwidth is the smallest. And then there's the maximum supported number of peers that we can compute is only 10,000. So which means that even though we can satisfy 82% of the demand, we can only serve 10,000 peers maximum with the previous assumption. So it looks like if we have streaming rates that are outstripping the actual average upload capacity, if we want to support more peers, intuitively we need more server bandwidth. So instead of given a fixed server bandwidth, if we do that, then we can only support a fixed maximum number of peers. That leads to the theorem, the main theorem of the paper. I put it exactly verbatim from the paper because that this is the only theorem that we have, and we do it in 3 different conditions. So if bar is actually the average capacity of the distribution is greater than P, which is the streaming rate. As you can see, U bar greater than P is the streaming average capacity greater than the streaming rate. Then the key observation here, regardless of the proof, is that the number of peers that can be served is unbounded. Given a particular bandwidth cost, and given an optimal streaming session for a number of served peers. And the corresponding delay, however, which is the number of hops from the server, to receive that data stream, obviously is not a fixed amount of delay. We increase that delay as we add more nodes, and that delay is increased as a logarithm of the ratio of the number of peers over the amount of server cost that we incur. In the second condition, if the two are exactly the same, streaming rate exactly the same as average upload capacity, then this number of peers that we can serve is still unbounded, but however the delay piles up. The delay to receive that stream is on the order of the linearly increasing of the ratio between the number of peers and the server cost. And in the final scenario where the average capacity is less than the streaming rate, then the number of peers can be served is bounded. We do have that kind of a reverse tree scenario in the previous illustration, regardless of the allowable delay. However, the maximum number of peers that we can serve increases linearly with the amount of server bandwidth that we put in to this system. Now, bear in mind that in reality, in any of the real-world peer-to-peer streaming protocols, right now, everybody is operating in the first category. In the category where the average capacity, let's say DSL average is 512 kbits per second, is always more than the actual streaming rate, which is usually tuned to something like 350, 400, and something like that. So, however, we do show that in the optimal case, in that case, in the first scenario, the number of peers we can support is unbounded. So all of the propaganda in the marketing wording of these peer-to-peer systems saying that we can support up to 200,000 peers, using only 100 megabits per second server, that's not a problem because optimally we can serve as many as we want. Yes.
So yeah, just have a quick question. I think you mentioned that in the analysis, there's no constraint on how many peers each node can connect, right?
That's right.
I see. So if there's such a constraint, that this picture might change, right? Even in the first category.
That's right. So intuitively speaking, it is quite intuitive. However, the implications here is that if we have average upload capacity that is greater than the streaming rate, then we can actually support an arbitrary large number of peers. But the delay increases as a logarithm for any constant throughput that we actually put in. And if we want to achieve the similar performance in terms of the amount of average delay that we have in the system, then we need to increase the server cost. We need to put in more bandwidth into the system, and that increase is increasing linearly with the number of peers that we need to serve if we want to keep the same delay, same average delay. if the amount of if the streaming rate is greater than the average upload capacity, then the number of peers naturally supported is limited, and the only option to support more peers is to actually burden the server with higher cost. And the next study that we would like to do is introducing some peer dynamics. So the previous studies, we assumed the static behavior, the static topology, everything is static, nobody leaves, nobody joins. Here, let's try to change the scenario and try to say, if we estimate let's try to assume that the peers can arrive, can leave according to a particular distribution. Well, how do we estimate the probability a new peer is accepted to a dynamic system? And the approach is kind of simple. It models the system as an MMNSQ, where NS is the maximum number of peers that are served in the system. And we assume, because this is MMNS kind of model, we assume that the arrival is a Poisson process, and there's an exponential length of time for the peer that stays in the system. So if we have this kind of a simple model of peer arrivals and departures, what we can do is that we can, depending on the behavior of a new peer, we can estimate two things. If we assume that a new peer, when they cannot be accepted in the system, when they're blocked, they do not retry. They just simply leave the system. Then the queuing system is an Erlang loss system, and the probability of the acceptance ratio can be estimated, similar to any of the previous papers on cellular networks with admission control algorithms. And if we assume that the new peers, when they join the queue and they wait as long as necessary until they're accepted, then it is an Erlang delay system, and the service waiting times can be estimated as well, instead of the probability of being accepted. So let's take the first scenario and try to take a look at one example. The example is that we can assume that we have a session with 3 million peers. Obviously, the 3 million peers, they don't come online at the same time. Each one of these peers, they tune in twice a day following some kind of a Poisson distribution, continue streaming for an average of 30 minutes of time following an exponential distribution. And then the upload capacities at each peer is constant at 300 kbits per second. Streaming rate is lower than that, is 250. And the user's required delay of no more than 16 hops. And let's say, try to predict the number of peers that we can actually serve at the same time. And that's over 170,000 peers that we can serve at the same time. And the probability of accepting a new peer into the system is extremely high. Yes?
Do you assume that if there's any change in the membership, the topology immediately organizes?
Exactly. So that's exactly what we assume. We assume that the topology immediately reorganizes at will, rearranged at will, can be at any time rearranged. There's no overhead in rearranging topology and nothing like that. However, in reality, it's not the case. So that's all theory, but exactly what kind of inspiration do we have? What kind of the heuristic can we actually design so that we can be inspired by the theory? So one of the things we can do here is that we can actually try to, in an intelligent way, organize the topology when the peer joins. So that's the best time we organize topology. When the peer joins, we need to have some kind of a placement protocol to place the peer in a part of the topology, in a particular location in the topology. For example, as one of the millions of different ways of placing a peer, following our previous instructions, one possibility, we can calculate the largest difference between the combined upload capacity of the k-hop peers and the bandwidth that is necessary, that is required to serve peers at the next hop, the k+1 hop from the server. And the largest difference between the two, if we can actually do that, we can calculate that difference. We pick the largest one, we insert the peer into that level. So if that difference is negative, we put it in the k-hop. If the difference is positive, we put it in the k+1 hop. It's a very simple heuristic. It's one of the many ways that we can design a heuristic based on the previous instructions from theory, inspirations from theory. keep in mind that previous theory also says we should push high bandwidth capacity peers closer to the source. So in this case, we should give some preference to the policy of placing peers with high bandwidth close to the source. So we should take that into account and use that as a weight in the equation that we use to calculate the location to put in the peer. If a peer had a large upload capacity, we should insert it higher up in the system. So without bothering you with all the figures and graphs and so on in the paper, as I just want to summarize the result to say it works. This heuristic works. Obviously, this is a very theoretical heuristic in the sense that this heuristic may probably never be implemented in the real world. However, if it is implemented, it is better than random topologies, better than tree-based topologies, in terms of saving the server bandwidth cost, which is our objective optimality. However, it is also orders of magnitude worse than the optimal ones, because the optimal ones, they assume we're kind of trying to sort the upload capacities. We try to push the upload capacity all the way up, and then sort them up so that we push them down, down, down. So this thing, because it does not have that kind of a global knowledge of sorting them, it is assumed that each peer had only a partial view of the entire system when it tries to do this kind of calculation. So it tries to take a limited view of the system, take a look at who is in the k hop, who is in the k+1 hop, compute the difference, the delta, and then try to insert it into that level. So it is not as good as the optimal one, but it is better, nevertheless, than the random and the tree-based. So let's take a look at lessons learned that we have here. So the first lesson that we have learned in terms of the theory that we have is that it is important to care about delays. So if we have delays in the sense that the number of hops from the server to the actual peer, it is important to care about either the average or the maximum delay, because the delay introduces longer difference between the time where the live event occurs and the time where we have the playback of that live event. And that is the downside of using peer-to-peer, because if we don't use it, we'll directly connect to the servers, the delays will be minimum. It is also possible to have higher streaming rate than the average peer upload capacity. So we show that if we put in more server bandwidth cost, we can support more peers, even if we have higher streaming rate. It is probably just required that we organize topologies in a better way. Assuming that the server bandwidth can make up for the deficiency of upload bandwidth and the demand for the streaming bandwidth. It is also wise, it's the third lesson that we have learned, to push the high bandwidth peers to the streaming source. And that is one of the things that we believe is not there in the tree-based protocols, and it's not there even for the random mesh-based protocols. What we wanted to do is that we want to push high bandwidth peers close to the streaming source. We don't want to randomly organize them, if we can do it. And if we have the streaming rate that is less than the average upload capacity, which is the case in all real-world protocols, it is possible to scale up to an unlimited number of peers. So the actual number you can scale up really depend on the deficiency of the protocol. If we have the perfect protocol, we can scale up to an unlimited number of peers. And finally, it is critical to consider new peer insertion. So when we insert a new peer into a topology, we should devise all our intelligence, all our algorithms right there. It should be carefully designed instead of randomly inserted or inserted into a tree or things like that. We should consider it to be an utmost important algorithm in any peer-to-peer protocol. Not the algorithm of buffer map exchanges, not anything else. New peer insertion into the topology is the most important. So if this is a paper, obviously it was a paper, then if given adversary in terms of reviewer, the reviewer could say, the disadvantages, the drawbacks, the main problem I have with this paper is, you don't have this optimality. There's no way for you to have this optimality because there's limited local knowledge, limited visibility. lack of global information. You have no idea what is the average upload capacity. You have no idea what's the server cost. You have no idea how many nodes are out there supported. Anyway, there's no global information. There's, if you do this, if you do require global information, you don't have scalability. So all of these are critical comments if this were a paper. But my question here, as a rebuttal to the actual comment here, is it really a problem? Do we really need to consider only the scenario where we have limited knowledge, limited visibility, limited information from each one of the peers? Is it possible that we have almost global information? I believe that it is possible. I believe that we should switch our focus from having a fully decentralized serverless protocol with only peers making local decisions to a protocol where we can take advantage of more than localized information. We can take advantage of global information. What's the reason? The reason here is that we could have a server right there, or more than one server, that keep track of all the nodes, inserting themselves into topologies, nodes who report their upload capacities, nodes who, if they're left with the server, will know in 5 seconds, and it still is not a problem because all of these servers operate using UDP. We have no problems of denial of service attacks to these servers. The servers also take advantage of such information to actually try to run a very intelligent and fast and high-performance algorithm to select the best way that a new peer will be inserted into the topology. And when the server gives, we can call it a tracker, we can call it anything, gives information to this new peer in terms of who this new peer should contact, this server has already made up all the choices, has already computed the best way, the best location to place this new peer into the system. So if we consider the possibility of such a high performance and huge server in the system, then we don't have to constrain ourselves with the local knowledge, with a fully decentralized algorithm, which seems like the focus of all previous papers. We should move ahead on designing a full centralized algorithm to organize topologies. And that is the end of the discussion. And my name can be searched. First name can be searched, google.com, life.com, ask.com. And all of them, the first link comes back to my homepage where you can download the paper. That's it.